the next. So for random vibration, as similar for, sorry, yes, yeah, doing still. Is it completed, right? Yeah. So the next is random vibration. Similarly for your harmonic analysis or what we call frequency response analysis. This response is like your loading is randomic. You don't know how your load is there. So how your load will be acting onto your component. Same vibration analysis itself, this is a random vibration analysis. So for this similar procedure we will follow. The only thing is we need to give the load as random. The load, the random points need to be picked and need to analyze. For that I have picked one of a problem. So as you can see this, a cantilever beam of 100 into 100 mm with Young's modulus, Poisson's ratio and density. Oh, sorry. Yes. So for this problem, that is for random vibration, so just took a reference of one of a book. Okay. So here for the random vibration of a cantilever beam, which is the load is acting to the structure at the one end. So how it is acting? So based on your PSD, what is PSD is like power spectrum distribution or density we call it as. So this is nothing but the point at each points your load is acting onto the structure. That is what it explains about, all about. Okay. So this you can see that PSD in it is gigahertz per gigahertz, that is gram cube per gigahertz, G cube by hertz. So we take this as into what we call as an input. For this input at each point, as you can see that 1, 2, 3, 4, 5. 5 points are there which are given as PSD inputs for particular densities or to the base values of PSD. So the response already they have mentioned here for the particular thing. This for the PSD your frequency response will give you in this manner where at this point it is a peak and the second piece at the peak at the other end. Okay. So for the similar thing, if you use to our software that is used for other different software. So if we use the same thing to our software, what exactly we get a result? So if I take same thing as a cantilever beam, considering that with 200 into 200 as a one cantilever beam of 100 or 1000 mm. So I'm just creating the same thing. One second. Sorry, this is the wrong one. So if I take the same thing with constraints of the length, so it is giving 20. So we require 200, or it is giving an mm. 1 second, let me check. Okay. Is short also, 20 or 200. Sorry, it is 100 into 100. Okay. So our dimension would be like 1000 mm length. So this is our beam. So same thing, at the same condition it has been given as a length of 1 meter as 1000 meter and E value is 2.1 or 210000 and then density is 8000 they have taken, and your viscosity is 0.3. For the same thing as a cantilever beam, again I will create a material with the same only width 210000 with Poisson's ratio as 0.3 and density as 8000 mm, in the sense it will become 8.0 e raised to minus 9. Okay, so your density as well as material has been created. So just all the procedure are same till step 2. So that is assembly, create an instance, step. Here for the step 1 we take as a frequency analysis again, that is your modal frequency analysis. For the same thing I will take again 10 as an output frequencies, and the second would be your random response analysis. Again here there are two types, that is random response analysis and random spectrum. So we are doing random response analysis, we are checking the response of the structure on the basis of giving a PSG as an input load. Okay, so continue. Here again low frequency, upper frequency and number of points. For the low frequency we have taken as 20, as in the low frequency the range is 20 to 2000 hertz. Okay, and damping, structure damping has taken as 10% and 10 modes required for 10 elements. Okay, so we will take 20 as initial and 2000 as upper limit. I will take 10 points and bias I will consider as 1. Okay, here it starts with the structural damping. Okay, so we are taken as structural damping. How many modes he has mentioned? They have mentioned from 1 mode to first mode to 10 modes, and the damping constant as 10%, in the sense 0.1. Yes, so we are mentioning a start mode and end modes. 10 modes we will get that. So damping constant as 0.1. So this creates your random response analysis. So I'll just rename them so that modal. So this we have created the steps. Now go to interactions. I'll say why I am taking this interaction. Okay, so I'll create one point, an extra point, as an just to give a response. Excuse me, sir. Hello. So just one point as a response to apply load, as well as to show you guys that MPC, how MPCs are created. Okay. I'll just delete this. Go to assemblies, features. That is not edit. So I'll take this 1020, the distance, or 200. So that would be better. So it will be clearly shown. Okay. So now it has created somewhere here at this distance. Now what I'll do an interaction with the point as well as the surface. That is, I'll create a MPC, a rigid body. So go to constraint, MPC, continue, set 1. So select a point and a surface. Now it will ask which type of element you want, a beam element, tie, link, pin, elbow. We don't use pin and elbow. We usually use tie or beam. Beam in the sense it will behave as a beam, as a cross section need to be mentioned, and it will be deformed. Whereas tie and link will not be a deformed one. Okay, so I'll take a tie. Now you can see that you got a point and MPC points are connected at each points, okay, on the surfaces. Yes. Now go to load. Load here, I'll apply a boundary condition for initial. Continue on the other side to constrain it as an encasters, and the same similar I'll take again for acceleration based motion. Okay. So which direction I want this body to move, which body direction I need to leave this. So I'll consider u2 because in y direction as it is been need to vertical, or you if you want an x axis you can consider u1, or in z axis you cannot use because it cannot be oscillated on the z axis. So I'll consider u1, and here u1 is considered, and the correlation whether your load is required with the correlation or not. So for that I'll specify the correlation. It is 1D, so I'll take it as correlated with your direction, and the PSD, power spectrum density, need to be mentioned here. So for that you can right click here on the same and create a PSD definition, or same thing, go to amplitude and select PSD definition here. Either you can do it. So I'll just, it's better to select here itself so that a PSD definition will be created. Now here a specification unit, what unit you want, a power or decibel or gravity, in which. So we are doing into SI system, so I'll take as a base motion as a gravity. So how much it will be? 9.81. Okay. So now the specify the data, real and imaginary and frequency, that is are required. The PSD values, real and imaginary, frequency versus your PSD values. So that is 0.002 at this point, and the first point is 0.02, that is a real value. So imaginary value will be always a 0, 0.02, and imaginary value is 0. What is the frequency at that point? 1 second, let me remove this. At that point we have 20 Hertz. Okay, so I'll take 20 Hertz as a frequency. The second point again, it is 5.053 with 52 Hertz of frequency. 053 with 52. Similarly, same thing again at 0.053 with the same point with 900 Hertz of your frequency. So 0.053, imaginary will be 0, and here 900. Next, the fourth point, which is this point. So it is 0.0022 for 2000 frequency. So this is given, the PSD definition has been given. So now just call that to this block as amp1. Now the real value, there is no need to multiplication factor as we are taking the same values. So I'll consider this as 1, and the imaginary we have considered all as 0, so there is no require, so I'll put it as 0. So I'll consider this is u2. Okay. Now next, coming to the boundary condition. Again, for the initial I'll take this as displacement here for this point, leaving u2, the other directions are arrested because the load will be acting onto the one direction. Okay. Now for the same thing, so this is Okay, so all the boundary condition has been established as well as interaction has been done. Now mesh. So I'll select part seeding. I'll take 10 or I'll take 5 mm so that we can clearly get the image. Oh, sorry, 5 is too fine. So 20 mm will be your element size. So the mesh is also generated. Go to job, create a job, and then give a submit. History output. Okay, one more thing. At the each step point, output required. So here, for the first modal analysis, your default output would be your displacement. You can also call stress, that is von Mises, or your stress component would be also fine for the model. As was the same thing for your frequency response, the default outputs are there, A, L, U, S. So for that particular, we can also take with the root mean square root, and for the stress, von Mises is sufficient. Okay, so this is the required output what we are requesting for our particular solution. Just give a submit. For 2000 frequencies, it gives you okay, it is done now. So go to results, you can check the stresses for your frequency response, the stresses value for each frequencies. As you can see this, for the particular stress, that is, as well as your displacement, U1, U2, U3. For the same thing, if I plot a graph with the path, I need to generate. Okay, 1 second. U2, any one point, okay. So active frame again you require for frame 1 for model, remove the model and apply, give a plot. So now you can see that your peak is 10 raised to minus 9, 2 or 2.25 something with the same thing. As you can see that we are getting the same range of 10 raised to minus 9 somewhere here with the 8, 9 with the frequency of 1000, sorry, frequency of 100. But exactly it is not matching. That is difference between each software what they built. So we are finding a peak at these, at this point, as well as this is a more peak. Yes, actually it should match exactly what it is shown in the graph. Due to few inputs or change in the element type and other things, we get this way. Yes, any doubt here? Any doubt? Fine then, try this one. If anything, let me know. We can make this correctly. Sir? Fine.